Nature is inherently non-linear, especially when it comes to how things grow and scale. One particular hidden code is responsible for financial market crashes, fat tails, and black swan events. It commands exactly how nature scales, from the relative strength of an animal to the infrastructure of megacities. An engine that drives the explosive winner-take-all network growth of YouTube channels and even Bitcoin. Most people see this explosive growth and assume it's exponential, but they would be exactly wrong. This is the domain of the power law, and it highlights a fatal mathematical error that scientists, investors, and policymakers make every day. In this video, we're going to break down the blueprint of a power law, show how it fundamentally differs from exponential growth, and learn the math gymnastics required to spot the difference before it's too late. The power law equation is elegant. First, we have x. That's our input. It's the thing that's growing or moving forward, like time or size. C is simply a number, acting as our baseline scale or multiplier. But the true engine of this system is the exponent, alpha. Depending on the value of alpha, the geometry of our power law is locked into one of three strict mathematical regimes. Regime 1 is linear growth, where alpha is exactly 1. A change in the input yields a directly proportional change in the output. It's the baseline of simple, independent, additive processes. If you put 1 unit of effort in, you get 1 unit of result out. Put 10 in, get 10 out. Regime 2 is called superlinear growth. When alpha exceeds 1, we enter the superlinear regime. The growth accelerates geometrically. The larger x gets, the steeper the slope becomes. This is the mathematics behind area to volume scaling and explosive network growth. Regime 3 is called sublinear growth. When alpha is a fractional value between 0 and 1, the system behaves completely differently. Whether it's an alpha of 0.5, which is the square root function, 1/3 for the cube root, or any other fractional power, this is the regime of sublinear scaling. It never stops going up, but its rate of growth constantly decelerates. This is the math behind why large animals have much slower metabolisms than small ones. One of the most common errors in science is confusing superlinear power law growth with true exponential growth. They both exhibit rapidly accelerating curves, but their underlying generating mechanics are fundamentally different. Before we dive into the math, there is a critical distinction we need to understand about how power laws and exponentials impact the natural world. Both power laws and exponentials are fundamental engines for how almost everything in our universe scales. Crucially, a power law dictates how a single entity grows. A city expanding its borders, a network acquiring users, an animal evolving to be larger. In general, any system that is constrained by its geometry is governed by a power law. In the physical universe, we are trapped in 3 dimensions. As a system grows, it has to constantly negotiate the maths between its 1-dimensional length, its 2-dimensional surface area, and its 3-dimensional volume. Because surface area scales as x squared and volume scales as x cubed, any physical system that relies on both will inherently be governed by a fractional power law. The growing entity is fighting its own geometric shape, and the exponent is the mathematical fingerprint of that fight. But what about the internet, or wealth distribution? They don't have physical volume, but they do have geometry. In mathematics, this is called topology. A network is constrained by the abstract geometry of its connections. A new website cannot connect to every other website simultaneously. It must navigate the existing hubs and links. Because growth is constrained by this network structure, it generates a power law. By contrast, when you are dealing with an exponential, you are no longer bound by a single geometry. You're looking at self-replication. It's 1 bacterium becoming 2, becoming 4, becoming 8. It's $1 in a bank account earning interest, and then that interest earning its own interest. There is no dead weight. When 100 bacteria divide into 200, all 200 are actively participating in the next round of growth. Now, let's see this in the math. In our power law on the left, the exponent is a static number. In this case 3 to represent our 3 dimensions. Now, by differentiating, we can see that the system's rate of growth is proportional to x squared, the dimensionality of surface area. Proof that a solid object expanding its volume is limited by its own 2-dimensional boundary. And in general, the growth of any power law is structurally constrained by its own geometry. In the exponential function on the right, The variable x is the exponent. Again, by differentiation, the system's rate of growth is proportional to the function's own current state. dy by dx is proportional to y. This is unconstrained self-replication. Let's put them in a race. In the blue corner, representing power laws, y equals x cubed. And in the red corner, representing exponential replication, y equals 2 to the power of x. Once they gain momentum, the power law completely crushes the exponential function. If you stopped looking here, you would think power laws rule. But exponential growth has a secret weapon: patience. Because it is constantly multiplying its current size, it doesn't just grow, its rate of growth grows. Look further into the future and the power law is left in the dust forever. As x approaches infinity, an unbounded self-replicating engine will always dominate any polynomial power law. In other words, a system constrained by its own structural geometry will always eventually be overtaken by a system that self-replicates. So we know exponential growth will always win the race. But here is the problem that scientists face every day. In the real world, data is messy. If you just see a curve shooting upwards, how do you know if it's driven by the geometry of a power law or the compounding engine of an exponential? To the naked eye, a fast power law and a slow exponential look exactly the same. To figure out what we're looking at, we need a mathematical transformation tool. We need a way to neutralize the compounding effect of the exponential. We do this using a logarithm. Let's apply this to our graph, beginning with a semi-logarithmic transformation. If we take the logarithm of an exponential function, the variable x is pulled out of the exponent. The resulting equation, log y equals x times log 2, maps perfectly to the standard linear equation, y equals m times x, where the intercept is 0. Now watch the y-axis. Instead of counting linearly by thousands, we are going to crush the axis so it counts by powers of 10. By transforming only our y-axis into a logarithmic scale, true exponential compounding will always reveal itself as a perfectly straight line. But look at our power law. It can't handle the transformation. It bends and droops, proving it doesn't have the compounding engine needed to keep up with the logarithmic space. We use a log linear plot to catch our exponential function, but to catch our power law, we need to take our coordinate transformation one step further. So let's apply the exact same mathematical trick to our power law and take the logarithm of both sides. By the rules of logarithms, that exponent, the 3, drops down to the front. Look at what we're left with. Log y equals 3 times log x. This is the exact formula for a perfect straight line, but this equation reveals something profound. In a fully logarithmic coordinate system, not only will the power law become a straight line, but the slope of that line will be exactly equal to the system's scaling exponent. This is why log-log plots are the foundational tool of complex system analysis. If you map earthquake magnitudes, city populations, or the wealth of billionaires on standard axes, it just looks like noise. But if you plot that data on a log-log graph, and it forms a straight line, you know instantly that you've discovered a power law. You have found the hidden geometry of that universe. If you enjoyed this video, please like and subscribe, and I'd love to hear your thoughts in the comments.